This is Dr. Fred DiPiero, and this video is on analyzing circuits that contain dependent sources. Learning objectives are the analysis of such circuits with the dependent sources, and more generally, the ability to accommodate dependent sources in any circuits analyzed by any technique. Prereqs are the ability to analyze circuits that include independent sources. Now, why do we need these devices? Why would we want to do this? Well, dependent sources can be used to model complex circuits such as amplifiers. This is very helpful as the functionality of a more complicated subsystem, like an amplifier, can be represented via simpler elements using the dependent sources. This is also helpful when modeling elements that are nonlinear in nature, such as transistors. The output of a dependent source varies. Dependent source can generate either a current or a voltage as its output. Note the symbols on the right. They all have a diamond shape, indicating they are dependent sources, not independent sources. Now, where the independent sources provide a constant output, the output of a dependent source is going to vary, and it's going to be determined by some other signal in the circuit. That might be a current or a voltage. In these upper two examples, we see the diamond shaped with the plus-minus polarity, indicating that these dependent sources generate a voltage as an output. That voltage in the first case is controlled by another voltage. You see a constant K times some other voltage VB. K is often given in an introductory type of problem. We can also have a dependent voltage source that's controlled by a current, as the second case shows. K times IC, some other current in the circuit. The output of a dependent source can also be a current, which is controlled by a current or controlled by a voltage. In general, when we have dependent sources, an additional step will be added in an analysis. And here I'm thinking mostly of analyses involving methods of node voltage or mesh current. The dependent source is going to add another equation because it adds an algebraic step. The intensity of the source or output of the source is not a simple constant. Rather, it has an algebraic relationship with some other quantity in the circuit. Hence, an additional step in the analysis, but not too bad. Okay, back to the issue of why we would need to use these things. Again, they produce much simpler models. Here's an example of a single transistor amplifier. FYI, transistors were discovered by Bell Labs in 1947 and commercialized shortly thereafter by RCA into commercial products. This revolutionized electronics. You see the bipolar junction transistor in the center of this circuit. Now, transistors are inherently nonlinear, making them harder to analyze. We can create a linear model that describes the transistor's operation over a narrow range of operating conditions. We can do that using a dependent source as shown here. Having a linear model means that we can readily obtain solutions to large circuits, for example, by solving linear equations simultaneously. Here's another example. This is an operational amplifier, or op-amp, 741 type, an industry standard. These are very, very useful in implementing mathematical operations such as add, subtract, integrate, differentiate, and others. Now, this is rather complicated internally, no doubt, but from an external perspective, we can describe it as such with two inputs, VP, VN, and Vout, and all that more complicated arrangement internally can be described can be approximated, let's say, using a single voltage-controlled voltage source You see the inputs VP and VN are ideal. The wires just come in and end, so there's no current entering the device in this idealized model. And the output is determined by this dependent source. It's a parameter A times the voltage difference. These are node voltages, VP and VN. The difference in those node voltages times A, and take A to be a large number that can be in the millions depending on conditions. So, circuit models with dependent sources can be much simpler because they hide those internal details. Very helpful. Here's a quick example that illustrates the algebraic substitution in order to handle a source dependency. I'm showing two blocks here. The first is a signal source and the second is an amplifier. And the dependent source is describing the operation of that amplifier. Note that the output voltage here can't be determined directly. We don't have a specific value associated with the dependent source at this point. It depends on another voltage, in this case, the node voltage V2. And specifically, V out is 50 times V2. So, given the dependent source has this definition, V out is 50 times V2, and we can use a voltage divider at the input section in order to get V2. Vs times this fraction established by these given resistor values makes V2 equal to 2/3 of this signal input Vs. Then applying the algebraic relationship associated with the dependent source gives us a value for the output of about 33 times Vs. We could then substitute any value we want for Vs and get the output for a particular case. Okay, so this was an introduction to dependent sources, giving you a feel for how to analyze them and how to accommodate these kinds of sources in any circuits, in any circuit analysis technique that you may be learning.